Good morning, students. Today we are going to see chapter 14, light emitting diodes. In the previous class, we have studied about the photoelectronic junction devices. On that, diodes, photodiodes we have seen. Second part is light emitting diode. What is light emitting diode? It is a PN junction diode which is heavily doped. While under forward bias, it will emit spontaneous radiation of its own. It is going to emit spontaneous radiation of its own. The diode is covered with a transparent cover. The diode is covered with a transparent cover so that the emitted light will come out automatically. The emitted light will come out automatically. When the diode is on forward bias, the electrons are moved from negative side to positive side, that is N junction to P junction, and holes sent from P to N. Holes will be moved from P to N. Thus, at the either side of the junctions, PN junction diode on either side of the junctions, excess minority carriers will combine with the majority carriers, in N junction, which will be the majority carriers and which will be the minority carriers. In N junction, negatively charged, that is electrons. P junction, positively charged. Okay. So, while recombination, energy will be released in the form of photons. The minority carriers and majority carriers combine, and that at the time of recombination time, energy will be released, and energy will be released in the form of photons. Energy will be released in the form of photons, and this photons have the energy equal to or slightly less than that of the band gap. Band gap we have studied, the gap between the valence band and conduction band. So these have energy equal to that. The energy released, photons of energy released have equal to that of slightly less than that of the band gap. Here the forward current of the diode is small, and then the intensity of the light emitter will also be small. If the forward current of the diode is small, means then the intensity of the light emitted will also be small. If forward current increases, intensity of the light also will be increased, and it will reaches the maximum. Further, after reaching the maximum, if we increase in forward current, the intensity of current will decrease. After reaching the maximum, if further it is further it is increased, means the intensity will decrease. So, LEDs are biased such that light emitting efficiency will be maximum. LEDs are biased such that the light emitting efficiency will be maximum. And the reverse breakdown voltage of LED is 5 volts. The reverse breakdown voltage of LED is very low. It is of 5 volts. So, what we have to do is, we have to take care that high reverse voltages do not appear across them. If high reverse voltage appears, means it will break down. So, we have to take care that it should not have high reverse voltage. And different types of different colors of LEDs are available. The colors are red, yellow, orange, green and blue. These colors of LEDs are available. The band gap of LED should be at least 1.8 electron volt. The band gap of LED should at least be 1.8 electron volt. And then the spectral range of visible light. The spectral range of visible light must be 0.4 micrometer to 0.7 micrometer. That is 3 electron volt to 1.8 electron volt. That should be equal to 3 electron volt to 1.8 electron volt. To make different colors of LED, we use gallium arsenic phosphorus. To make different colors of LED, we are using the semiconductors, gallium arsenic and phosphorus. And if we need red light, means we are using in the gallium arsenic it will be gallium arsenic 0.6 and phosphorus 0.4. Here the energy gap will be 1.9 electron volt. Here the energy gap will be 1.9 electron volt. In infrared, if you need infrared LED means we are using gallium arsenic of energy gap 1.4 electron volt, 1.4 electron volt. So these are the points about the LEDs, light emitting diodes, light emitting diodes. Then what is the uses of LED? What is the use of LED? I think you know about all these things where you are using the LEDs in remote controls, in burglar alarms and optical communication purposes we are using the LED. In these fields we are using the LED. Then what is the advantages of LED? What is the advantages of LED means? It works in very small voltage. If you are providing a small voltage itself, it will works. That is low operational voltage, and power will also be less. In less power it will be working and it will act fast. Normal tube lights and all, normal lights and all, if we are switching on means it will take some time to switch on, but this will act very fast, that is fast action, and no warm up time required, and the bandwidth of the emitter light is of 100 Armstrong units to 500 Armstrong units, 100 Armstrong units to 500 Armstrong units, and it is having long life and ruggedness, and then fast on off switching capability. It is having the fast on off switching capability. For all these 5 advantages, we are using LED instead of normal lights. Then we can go for solar cell. What is meant by solar cell? Again it is a PN junction diodes. PN junction diode which generate EMF when solar radiation falls on it. It is a solar cell is a PN junction diode which generates EMF when solar radiation falls on it. If you are keeping a PN junction diode on a sunlight, it will receive the solar radiation sunlight and it will generate EMF. Okay. So the structure is given there. See the diagram. This is a there is a p-type semiconductor of about 300 micrometers, and there is a n-type silicon wafer is formed, thin layer of 0.3 micrometer. This is formed by the diffusion process. This thin layer is formed using the diffusion process. There are different types of process are there, etching process and diffusion process, and different types of process are there. Here we are using the diffusion process to form the thin layer of n-type layer on the surface of the p-type layer, The thickness of the p-type layer is 300 micrometers and the thickness of n-type layer is of 0.3 micrometer. Okay. So the other side of p, see here, this is the p-type layer. It is of thickness of 300 micrometers, and this n-type layer is of thickness of 0.3 micrometers, and the other side of silicon is coated with a metal. This one, metal coating. It is called as back contact. On the top of the metal, we are having finger electrode deposited. It is of the very small fractional area. That is only we are having thin lines. So here what we are doing is light radiation is make to fall on the surface of the semiconductor, that is on the top of P, on the top. Okay, so here three basic process of generation of EMF is going on. Three basic process of generation of EMF is going on when lights fall on the solar cell. What are all the three steps means? One is of generation, another one is of separation, and another one is of collection. Generation, separation, and collection. Three basic processes going on when the light rays, sunlight falls on the surface of the p-type semiconductor. When the light rays falls on the surface of the semiconductor. So here in the generation step, generation of electron and holes, that is called as EH pass, due to the light close to the junction, it will move on to the junction. So generation of electron and hole pass due to the light close to the junction, that is when light rays falls on the surface of a PN junction, electrons and holes are created. Okay. So the next step is separation. Here the separation of electrons and holes due to the electric field of the depletion region. In the depletion region we are having electric field. Due to that electric field, the electrons and holes are separated. So electrons swept from N side, swept to N side. Electrons will move towards N side, and holes to P side. Holes will move to P side, and electrons will move to N side. Okay, and the third step will be the electrons reaching N side will be collected by front contact. The electrons reaching N side will be collected by the front contact, and holes reaching P side will be collected by back contact. Here we have here the back contact and front contact. We have back contact is the base, and this is the front contact. So the electron reaching N side will be collected by the front contact, that is top contact, and the holes reaching P side will be collected by the back contact. Okay. So what happened? Because of this, the P will becomes positive. Positive, and N will become negative. So giving rise to photovoltage. This will give rise to the photovoltage. So when an external load is connected, as shown in the diagram, here the external load is connected. A photocurrent of IL flows through the load. The photocurrent of IL is flowing through the load. IV characteristics of a solar cell is, we have drawn the IV characteristics. We have drawn. So what will happen? In the fourth quadrant, the solar cell is in the fourth quadrant of the coordinate axis. It will present in the fourth quadrant of the coordinate axis. The solar cells are fabricated with semiconductors of band gap 1.5 electron volt. The solar cells are fabricated with the semiconductors of band gap 1.5 electron volt. See here some of the examples are given, which are all having which energy gaps. Silicon is having the energy gap of 1.1 electron volt, and gallium arsenide is having the energy gap of 1.43 electron volt, and cadmium, tellurium having the energy gap of 1.45 electron volt, and copper indium and selenium having the energy gap of 1.04 electron volt. Okay. So, we are having some basic criteria for the selection of the material for solar cells. We are having some basic selection criteria for selecting a material for the solar cell. Selecting a material for solar cell. What are all the basic criteria? Means one is of band gap. The band gap should be of 1 to 1.8 electron volt, and the optical absorption should be very high, that is of the order of 10 to the power of 4 centimeter inverse, and the electrical conductivity should be considered. Electrical conductivity of the material should be considered, and the availability of the raw material, whether it is available in easy, and the cost should also be very low. Cost should also be very low. And these are the things to be considered while selecting the materials for making a solar cell. Then what is the use of the solar cell? The solar cell is used in power electronic devices, in satellites and space vehicles, and also in calculators, etc. These are the some of the examples. One is on satellites, and it is on space vehicles, and in calculators also we are using. So, this is about the solar cell. We have studied in the optoelectronic devices. We have studied about the solar. We have studied about the LED and solar cell, light emitting diodes, and about the solar cell also. So, now we can go for the digital electronics and logic gates. Digital electronics and logic gates. From the heading digital electronics itself, we can understand it is a digital one, that is of digital signals. We are having two types of signals. One is of analog signal, another one is of digital signal. One is of analog signals and another one is of digital signals. What is meant by analog signals? It means we should have continuous form of signal. We should have a continuous form of signal, that is time varying voltage or current. Time varying voltage or current. That is in amplifiers and oscillators, we are using signals in the form of continuous one. It is time varying and time varying voltage, or it should be time varying voltage or current. Okay, this is of the analog signal. If it is of digital signal, means it is of on the pulse waveform. It is on of the pulse waveform. That is, we are having only two different values. One is of 0 and another one is of 5 volt. One is of 0 and another one is of 5 volt. 0 volt is represented by 0 and 5 volt is represented by 1. We are having only two discrete values, 0 and 1. It is not continuous continuous flow of signal. Okay. So, it is called as digital signals. It is called as digital signals. Using this digital signals, we are having on circuit connections, that is of logic gates. We are using on circuit of logic gates. This logic gates is a basic building block of digital electronics. This logic gate is the basic building block of digital electronics. It is used in calculators, digital watches, robots, and industrial control systems, and also in telecommunications, system, and also this is about the logic gate. Logic gate is the basic building block of digital electronics. Now we can see what is logic gates. It is a digital circuit that follows certain relationship between the input and output voltages. Input and output voltages. What we are going to give is the input voltage. What is the output we are getting is the output voltage. So, common logic gates are NOT, AND, OR, NAND, and NOR. So, how many gates are there? 5 gates are there. One is NOT gate, AND gate, OR gate, NAND gate, and NOR gate. Okay. See here. First one is the NOT gate. It is also called as inverter gate. We can see why it is called as inverter. Here we are having the diagram for NOT gate. NOT gate diagram is the triangle with a bubble on the front, triangle with a bubble on the front. Okay. So, here we are having the input A and output will be the Y, input A and output will be the Y. Okay. So, only one input and one output, we are having only one input A and only one output Y. Okay. This, in this gate, if we are giving a input, means the output will be the inverted one, output will be the inverted one, so that it is known as inverter gate. So, it is called as inverter. See, if you are going to see, this is called as the truth table, this is called as the truth table. In this truth table, this is input and this is output. What the input is, if you are giving 0 as input, if you are giving 0 as input, the output will be 1, it is inverted, it is inverted. If you are giving the input as 1, the output will be 0, the output will be 0. Okay. So, it is giving the inversion of the input, so it is called as inverter. The formula we can have it as y is equal to A dash, y is equal to A dash. Okay, this is about the NOT gate. Then we can go for OR gate. OR gate will have 2 or more inputs. It can have 2 or more inputs and the output will be 1. Output will be 1. And if any of the input is high, if any one of the input is high, means if any of the input is high, the output will also be high, the output will also be high. Okay. So, we can have the formula as y is equal to A plus B, y is equal to A plus B. See here, the input values and output values, A and B, 2 inputs are there, so that we are having it as A and B. If A and B both the ones are 0, means the output will also be 0. If 1 is 0, first input A is 0 and input B is 1, means input B is 1, means the output will be 1. If A is 1 and B is 0, means it will be, output will be 1. If both the inputs A and B are 1, means the output will also be 1. Okay. So, this is about the OR gate, this is about the OR gate. Then we can go for AND gate, then we can go for AND gate. So, what is meant by AND gate? It is a symbol of D, it is a symbol, the symbol must be like D. If here we are giving 2 inputs A and B and the output will be Y, 2 or more inputs and output will be only 1. Here we can go for the truth table. First we can see about this formula, y is equal to A dot B, that is the output will be of the multiplication of the 2 inputs, output will be the multiplication of the 2 inputs. If A and B or both A and B are 0, means the output will be 0. If any one of the input is high, means output will be 0. See here, these are the examples. If both the inputs are high, means it will also be, output will also be high, output will also be high. Then if we go for NAND gate, what is meant by NAND gate? The basic gates we have seen as OR and NOT gates. OR and NOT gates are the basic gates. Here this gate, NAND gate, is the combination of 2 gates. NAND gate is the combination of 2 gates. From the name itself we can find N plus AND, that is NOT plus AND, NOT plus AND. Okay. So, the symbol of this NOT gate, what is the symbol of the NOT gate? It will be a triangle. Here we can see, here we can see it is a triangle. See here, in the NAND gate, that bubble in the front of the NOT gate can be drawn here. bubble on the front of the NOT gate can be added here with that of AND gate. This is the AND gate symbol, and a bubble from the NOT gate can be added here, so that it will combine, it will show the symbol of NAND gate, NOT plus AND, NOT plus AND. Okay. So, here the formula will be y is equal to a dot b bar b bar, a dot b the whole bar, dot b the whole bar. If you go for the truth table, a and b inputs and y will be the output. If both the inputs are low, means 0 into 0, you will get the output will be 0. If it is whole bar, means it will 1. And if any one of the input is high, means the output will also be high. See here 0 1 1 1 0 1. If both the inputs are high, means the output will be low, output will be low, that is 0, that is considered to be 0. So, this is about the NAND gate. This is about the NAND gate. This NAND gate and the next gate, NOR gate, is called as universal gates. Universal gates, because this can be derived by using the basic gates. Using this gates, we can derive the basic gates. Using this gates, universal gates, we can form the basic gates. We can form the basic gates also. Okay. So, next we can go for NOR gate. Next we can go for NOR gate. NOR gate means, from the name itself we can find NOT plus OR gate. NOT plus OR gate. The symbol is given here. It is a OR gate plus NOT gate. OR gate plus NOT gate. OR gate symbol. For NOT gate, we are using the bubble. We are using the bubble. The formula will be y is equal to a plus b the whole bar. A plus b is the OR gate formula, and the whole bar is for the NOT value. Whole bar is for the NOT value. So, inputs a, b and y, input a and b, output will be the y. Then if both the inputs are low, that is 0 0, means output will be high, output will be high. And if any one of the input, whether a or b is high, means the output will be low, that is 0. If both the inputs are high, high, means the output will be low, Okay. So, this NOR gate is also a universal gate. NOR gate will also be a universal gate, because again the same definition, by using these gates we can build the basic gates. Using NAND gate or NOR gate, we can build the basic gates or and NOT gates, or and NOT gates. So that this is called as universal gates. Or and NOT gates are called as basic gates, and NAND and NOR gates are called as universal gates. Why it is called as universal gates? Using this NAND and NOR gate, we can build OR and NOT gates. Okay, students, we have completed this topic. Theory part, numerical part is still pending. We can see in the next class. Thank you.